Can we do linear algebra with polynomials? Those aren't linear. Actually, we can do tons of stuff with linear algebra. One of the reasons that makes it so useful is that it applies to any situation where there's addition of things and scalar multiplication. Let's just talk about polynomials of degree less than or equal to 2. I've got a couple examples in here. And notice that when I add polynomials together, I get another polynomial. If I scale any of these by some scalar, I get another polynomial. We really could just think of these as vectors. Now I'm going to remove the arrows because it's a little bit complicated, and it's actually better to just think about them as polynomials, because what I'm going to do is apply a transformation. Now how do we transform polynomials and get another polynomial? My favorite way to do that is to take the derivative. So what I'm saying is that this input is going to get transformed to the derivative, which is over there. And this input over here is going to get transformed to that. And then a couple different inputs are actually going to go to 0. And it's actually a linear transformation because taking a derivative respects sums and also multiplication by scalars. And we can ask all sorts of interesting things about this transformation. What is the kernel of it? What stuff is going to go to 0? Previously, we saw that 0 and 3 both are going to map to 0, so they're definitely in the kernel, but can you think of anything else? We can also talk about the range, which is a set of all outputs that actually occur. I think earlier we saw that this occurred as an output, and so did this one. But can you think of a reason why x squared will never be an output of this function? Remember, our domain is only polynomials of degree less than or equal to 2. Maybe you figured out that the kernel is exactly the constant polynomials. Those are the only things that are going to go to 0. And maybe you also figured out that the range is a set of all polynomials a plus bx. In fact, put in the comments an explicit formula for what thing up here on the left would exactly go to that polynomial. This might seem like a fun game to play, but what does it have to do with matrices and linear equations? That's what linear algebra is, right? I got you, but we got to think about a basis. So if we think about things like 5x plus x squared or 3 or x minus 4, really we can just keep track of the numbers that are in front of the letters. Formally, what we're doing is we're picking a particular basis to look at what the coefficients of 1, x, and x squared would be, and we can just encode this data as a column vector. And so even though we're working with polynomials, we could just as well work with column vectors, and all of the arithmetic would be the same. For instance, add any vectors together as polynomials, you'll get the same answer as if you added them as vectors. So now let's think about our transformation. If we think about what it does to a polynomial, it just takes the derivative that we know from calculus. But if we think about it in terms of coordinates, what's going on? Inherently, if we put as an input the vector a, b, c, we've got to get the derivative, I guess, b, 2c, and then there's no x squared term, right? Pause the video and make sure you understand this, because we're about to go and say that actually this is just a matrix transformation, right? If we want input ABC and output that thing, then the only way to do that with a linear transformation is with this matrix here. So in other words, that totally abstract operation at top about polynomials and derivatives is really the same as just the standard linear transformation by this matrix. In fact, if you want to go through the algorithms you learned for finding, say, the null space or the column space or the range of a matrix, you'll see that the answers you get are exactly as the same as the ones we got before once you do the translation back to polynomials. This is why linear algebra is so powerful, because it applies in so many different situations.